I need to clear up some information in regards to the Q count discussion that we had um, earlier. So, in a previous episode, we talked about the Q families on the GPU, and we had a graphics and compute queue, we had a transfer queue, we had a compute queue, we had a um, video decode queue, a video encode queue, and optical flow queue, right? And I just wanted to rehash the discussion uh, on the queue count. The queue count. What queue count is how many basically it's how many submission timelines does the queue family allow. So for family 0, it allows 16 lines of submissions, right? um these lines of these are just, it's submission lanes, but it's not threads, it's not hardware units. It's not indicative of parallelism necessarily. um it's it's simply the number of available. Yeah, more queue counts does not automatically mean more parallelism, right? It is sort of a um it means the device exposes up to 16 independent submission queues that all support the same capabilities. Okay, so it's a very important thing to understand. All it means is that, for example, the CPU can submit something on one lane. The GPU can submit something on another lane. Maybe the driver itself uses a third lane, but it's just work being lined up to be processed by the queue family. It does not mean parallelism. All right. It's the VKQ handles, right? The VKQ handles. So Vulkan has these handles. So the GPU driver allows you to create up to 16 VKQ handles from this family. In this particular case, each of those queues support graphics and compute and transfer, right? Right. Each VKQ is an independent submission timeline. Okay. This does not mean 16 Q count is 16 and it has a graphics and compute and transfer and sparse capabilities. It does not mean 16 GPU cores. It does not mean 16 wave fronts. It does not mean 16 streaming multiprocessors. It does not mean 16 hardware schedulers. It does not mean 16 threads executing shaders. All it is independent submission timeline. That's it. The queue is gonna the queue is gonna it's the queue family is gonna stack them up and as work to be done. There might be opportunities for parallelism, but that is not guaranteed and that is not automatic, right? Um, Another thing that I wanted to more queues does not automatically mean more parallelism. Um, why would a GPU expose 16 queues? Okay, so why would a GPU expose 16 submission queues for this queue family and for this line of work? It's mostly for latency hiding and workload partitioning, not raw parallelism. Common reasons: multiple threads on the CPU submitting work in parallel. Okay, separating long running compute from short graphics work. Okay, async compute overlapping with raster. avoiding CPU side contention on a single VK queue, right? So basically, the CPU can submit multiple VK queues to this queue family, and be done with it. The GPU and the queue family will deal with the rest. The CPU doesn't have to manage it on its end. It doesn't have to like juggle the 16 lines of work on its side and submit it one by one. It sort of does the VKQ, all 16 VKQs, and the GPU will figure out how to actually process everything. But again, it does not automatically mean parallelism. So for example, if you have three submissions on this queue, Q0 could be the main graphics, Q1 could be async compute, example particles, culling, skinning, and Q2 could be background compute, streaming, pre-processing, and then the remaining queues unused or reserved for driver slash runtime. You almost never want to use all 16 explicitly, right? The queues, this queue count doesn't map one-to-one to hardware in any way. Um, what else? Okay, so what happens if you use two queues from the same family, right? So let's say we use two queues from here. Let's say QA is graphics and QB is compute, both from the same family, right? So there you submit work. One is from graphics to one is for graphics to one second. A is for graphics, B is for compute. Um, but and they're both being submitted to this queue family right here. Uh, Submissions to A and B are independent, right? So we have more than enough lanes, submission lanes, in order to accommodate that. Submissions to A and B are independent. GPU may execute work from both simultaneously. Operative word is may. You must use semaphores if one depends on the other, right? So obviously, you guys know GPU synchronization. You have to use semaphores if they depend on one, the result of one to the other, etc., etc. No queue family ownership transfer is needed because it's the same family. Um, there was one other thing I wanted to. There was one other thing I wanted to talk about. It was talking about the need for synchronization. Because the thing is that, so what I was saying is that, right, so what I was saying is like, hey, can I submit two processes, on this queue family that are not mathematically dependent on each other, right? They're not mathematically dependent on each other. um like, and can I just expect that they would run simultaneously and run to its maximum capacity, because it's not one submission is not dependent to the other submission. um this was an important teaching lesson for me. Mathematically independent is not the same as no synchronization. Okay, so even if the math is independent, sync can still be needed due to shared resources. For example, same buffer image used by both. If it's the same buffer and image, you have to do synchronization, because obviously they both can't be working on the same asset at the same time. Same memory being written by one and read by the other. So if those two processes are dealing with the same memory, then you're gonna have to deal with that. Same swap chain image frame buffer attachment, right? So if you're dealing with one frame, and these two processes have something to do with that one frame, then you're gonna have to do sync, right? Same descriptor set or dynamic offsets being updated by CPU while GPU is using it. Um, Same command pool, command buffer reuse. CPU synchronization via fences. If there's any write then read or write then write relationship, you need synchronization. Even if it's read only by both, you often can run without synchronization between them, but you still must ensure the resource is in a valid state layout and not being mutated elsewhere, right? So, I mean, I just bring that up because, again, guys, when you're dealing with GPU programming, you're dealing with parallel processing, and everyone wants to press that magical button and have everything run in parallel, and whatever process you have going, all 16 of them done in 1 second. But it's not that simple in GPU programming, and this is at the heart of the blessing and curse of GPU programming. Yes, you could run in parallel, but you have to make sure that everything that you're doing is not, they're not fighting for resources in one direction or another. It could be memory, it could be bandwidth, it could be a specific frame, a specific buffer, um, resources, what have you, RAM, all that stuff, right? So VRAM. So it's not as simple as just pressing the red button and having everything run to its maximum capacity. You're gonna have to deal with synchronization at some point. And I'm still learning, going through all these examples, all the different varieties of synchronization. Actually, on the compute n body example, which I'm working my way through now, we actually have on the compute pipeline, on the compute side of the compute n body algorithm, right? And it's just a bunch of particles that are moving around, and it's affected by gravity of all of the particles and velocity and all that stuff. We have two pipelines running on the compute side. We also have the graphic side because that's how we see the particles on the screen. But we have two pipelines running on the compute side, and we have to make sure that there's a barrier um, between those two pipelines, because the reading and writing of the same piece of memory has to be done in an ordered fashion, right? Because one hands off to the other, and vice versa, and stuff like that, right? So you really can't get away from synchronization. But anyway, guys, the main point of this video is that I wanted to clear up the Q count discussion, right? So I might have said that it was like 16 threads of work or 16 lines of things that could be performing simultaneously, and this means parallelism and all that stuff. I was wrong. This just means that 16 VKQ handles can be created, and 16 submissions can happen on this queue family at once, and that's all it means. It does not mean that it does not guarantee parallelism or anything else. It just means that you could submit 16 stuff to this queue family, and Vulkan and the API and the powers that be will accept those 16 submissions. Don't mean that the 16 submissions will happen at the same time in parallel. That's all up to the driver and the scheduler and the GPU and all that stuff, right? But if you have 16 things that you need to do, you will be able to at least submit them. Other things being fair, you would at least be able to submit them. Let's say from the CPU side, and then let the powers that be deal with what happens next. But at least on the CPU side, you'll be able to submit those 16, and go about your business on the CPU side. If let's say, for example, you had 16 stuff to submit, but you only had a Q count of 1, then things get tricky, because now you on the CPU side now has to manage, okay, which one are you going to submit first, and then you're going to have to wait for that process to be done. so that you could submit the next one and all of that stuff. But you could simultaneously submit things to the Q family, but it does not guarantee anything else. And it does not guarantee parallelism. This is Code Education. Thank you guys for watching. If you want to be able to run this stuff on your machine, tutorial number 1, install the Vulkan SDK on your machine. Tutorial number 13 is to install a bunch of examples. Want to make sure you have a Vulkan-capable GPU on a Windows-based machine. You could run on yeah, you know, if you buy a modern computer, a lot of times the integrated graphics will also be able to run Vulkan. But make sure you research it first before you make the purchase. Make sure you research it first and make sure it can run Vulkan. Right? The RTX cards on Nvidia can run Vulkan. Don't know about AMD and Intel, but I do know like the modern computers, the integrated graphics is able to run Vulkan. But you have to do your own research and check that out for yourself. Anyway, guys, this is Good Education. Thank you for watching. Have a great day.